हेलो क्लास 10th 12th नहीं 10th है. Okay, hello class 10th. We are starting the last part of the chapter 2. In the last section we had completed about the power, potential energy, kinetic energy and many more. Today we will talk about the law of conservation of energy in the body which is falling down, and in the simple pendulum, and next dissipation of energy and energy conservation too. Now, our new topic is law of conservation of energy, that defines energy can neither be created nor be destroyed. It only can be transformed from one form to another. We are going to prove this. Suppose um, an object at some height, it is going down at some place in between. Suppose that one was A, this one case is B, and after some time again it comes to C position. So we have to prove that the energy at point A, B and C in all the cases remains same. And what will be that? Let's calculate it. Here I am going to start the law of conservation of energy in mathematical form. For that, let a body of mass m at position A and at height h from ground. So what is the energy in starting? This ball is just going to fall downward. So here see, this ball is going to fall down toward the earth. This is the surface of the earth, and initially its velocity is 0. So first of all, what we have to prove, the energy of in this object at A and at just before touching the ground and somewhere in between that, at every position the total energy, the energy of the body is same, means conserved. For that, let us calculate first the energy, total energy at point A. Total means mechanical energy, and that is sum of kinetic and potential. So I'm going to first calculate the potential energy. So that is, yes, one more thing, remember my word, whenever you are calculating potential energy, remember my word, whenever you are calculating potential energy, just measure the distance from bottom to top, and whenever you are calculating the kinetic energy, just measure the distance from top to bottom, because object is falling in this direction. So if you are calculating kinetic energy, means during the kinetic position it is moving in this direction, at that time you have to measure the distance from top to bottom, and for the potential from bottom to top. So first I'm going to calculate the potential energy from bottom to top. This is the general equation of potential energy, that is mgh. So what is the mass of the object is, that is m. Let here the acceleration due to gravity is acting g. So value of g will be g still. And I said while calculating potential energy, measure from bottom to top. So what is the bottom to top distance? H. So you will put H. So you got potential energy here. What is that? mgh. Like make it equation 1. Now second part is to calculate kinetic energy. At A, I am writing here, at A. At A, we have calculated potential energy. At A, the velocity, initial velocity is 0. So this implies kinetic energy, that was half mv square. The velocity is 0. So kinetic energy becomes 0. Potential energy becomes mgh. So what is total energy? You can say total energy or you can say mechanical energy also. That is sum of potential energy and kinetic energy, that is mgh plus 0 gives you mgh only. This is total energy. So in this equation, if the total energy or mechanical energy of the object at A, total, because potential mgh, kinetic energy is 0. If the total energy at A is mgh, so what we have to prove? The object always has the potential energy mgh. Now I'm considering the ball is falling and somewhere, suppose here, it is right now, and we are going to prove here the potential energy and kinetic energy sum is still same. So for that, let's draw first. So here it comes from A to B. Now consider this distance from top to bottom, from here to here, bx, and what will be remaining from bottom to top now? h minus x. See here, the ball is falling with distance x, so remaining distance is h minus x. Now we have to calculate potential energy and kinetic energy at B. So first of all, I am going to calculate potential. So distance will be from bottom to top for potential energy. So you can see here at B means at this much. Potential energy was having the equation mgh. Here mass is same, g is same, but instead of h I said while calculating potentially from bottom to top, the distance is h minus x. So this is h minus x. Let's split it. So it becomes mgh minus mgx. I have calculated what? Only potential energy here. Now what we have to calculate? The kinetic energy. So to calculate kinetic energy, we must know the velocity here. Do you know the velocity here? The answer is no. For that, we have to calculate what is the velocity here. So I'm considering the initial velocity was 0 and here the velocity becomes v. So using the third equation of motion, distance is x here. Because I said while calculating the kinetic energy, we will take upper distance from here to here. So I'll take distance as x. So using third equation of motion, and that is, this is our third equation of motion. Initial velocity is 0 and 2gh instead of h, the distance traveled. What is the distance traveled from top to top here? It is x. So I'll write only 2gx. So what is becoming v square now? Only 2gx. Now we are having the value of v square. Let's calculate the kinetic energy using this equation. On putting the value of v square, that is 2gx here. So 2 will be cancelled. What is the kinetic energy now? The kinetic energy becomes mgx. So this is our kinetic energy and here it is our potential energy. Let's calculate the total energy. Total energy is equal to kinetic energy plus potential energy. Kinetic energy mgx from here and potential energy from here, mgh minus mgx. mgh minus mgx. So you can see mgx cancelled and the remaining is mgh only. So total energy at B is mgh. So as I said in starting, what we have to do, we have to prove that at every point the energy is same. At point A, we have already proved that at point A the total energy is mgh here. At point B, I have just proved that is mgh again. So at 2 points we have succeeded to prove. Only last point is here right now. So let the ball still falling further and comes to here. Here the body is, this is point C. Now the height from means to calculate the height. There is no height. It is just touching the ground. There is no height. So if h is 0, then potential energy is 0. Let's show in the equation. At C, h is 0 because this is just touching the ground. So h is 0. So at C, the potential energy. So at C, potential energy is 0. Now next, what to calculate? The kinetic energy. Come to here again. To calculate kinetic energy in this case, means the body is, now forget this point, the body is falling from here direct to here. Okay, the body is falling direct from here to here, from A to C. Distance covered h. Initial velocity 0. Here let velocity, final velocity is again v. We have to calculate the velocity while traveling from here to here because we have already calculated the potential energy. Motto is to calculate the final velocity, though we can the kinetic energy. So to calculate that using third equation of motion again. This is the third equation of motion. We are going to calculate the final velocity. Initial velocity is 0. 2 into g into h. H means the distance traveled. Distance traveled from here to here. What is the distance from here to here? H. So we will write direct h. What you got? V square is equal to 2gh. So we have the v square. Let's calculate the kinetic energy. This is the equation of kinetic energy. The value of v square 2gh. From here you can see v square is 2gh. So again 2 is cancelled. What remaining? Here it comes, the kinetic energy mgh. So let's calculate the total energy. Total energy is kinetic energy plus potential energy. And that is equal to mgh plus 0. And then last, total energy is equal to mgh again. So starting again from that point, see here, potential energy at A, mgh, kinetic energy at A, 0. Total becomes mgh. Potential energy at B from bottom to top is mgh minus x here. mgh minus x or mgh minus mgx. To calculate the kinetic energy at B, we have to use third order equation of motion. On using that, the distance traveled by the object from A to B is x. So it becomes V is equal to 2gx, and kinetic energy becomes, on cancelling 2, only mgx. This is potential energy, this is kinetic energy. On adding them, we got what? Total energy is equal to Ke plus Pe, mgx cancelled, only mgh. So at A mgh, at B mgh, and just we have proved at C also, what we got? Mgh again. So what it is proving? It is proving that the energy at every point in this equation, in this diagram, see, the energy at A, the energy at B, the energy at C, every point is having same energy. Instead, you can take any point in between here, here, here. At every point, you will get the sum of kinetic energy and potential energy remains same. What it proves? It proves that the law of conservation of energy. So we have seen in all the cases at all the points A, B and C, the energy remains mgh, means that is constant. This proves the law of conservation of energy. The same we are going to prove for the simple pendulum also. Like this diagram, you can see the three positions A and B and C. In those cases, the kinetic energy is maximum at mean position, while the potential energy is maximum at extreme positions. But at that same time, at the extreme positions, the kinetic energy is 0 because there is velocity 0. And at the mean position, the potential energy is 0 because h is 0. There is no height at the mean position. So there is potential energy 0. This also proves the law of conservation of energy, that energy remains constant in all the positions. If you're talking about in between, in somewhere in between the mid position and the extreme position, at that time there will be a kinetic energy and potential energy both. But what is that? We have to calculate according to the rise in height of the pendulum when it is swinging in any side. Okay. Now again, proving the same law of conservation of energy in the simple pendulum. This point A is called mean position, means this position is called mean position, and these two positions are known as extreme position in the simple pendulum. Comparing the positions in the extreme with the mean, so you can see there is a change in the height of h, means when the pendulum goes from this point to this or this point to this, it is covering some height, means it is gaining potential energy. So let's calculate first of all here and here the energies. Means first of all I'm calculating the potential energy at B and C. Consider the bob has mass m, and here the acceleration due to gravity which is acting is g. So when it gains some height h, so potential energy at B and C, potential energy at B and C both is mgh. Now see, when the bob goes toward this point, so first of all, while going from A to B, it decreases its velocity, decreases, and then comes to rest, and then toward this point A. So at B and C, what will be the velocities? See here, the bob is going up and up and up and up, and then 0, then it returns. So means at B and C the velocities are 0. So at B and C, kinetic energy at B and C. So kinetic energy at B and C, because of V is equal to 0. See again, V is equal to 0 at these 2 points. So the kinetic energy, so kinetic energy 0, means potential energy at B and C, kinetic energy at B and C is given here. Potential energy is mgh, kinetic energy is 0. So what is total energy right now here? Total energy is equals to again mgh plus 0, again mgh. So you can see at point B and at point C, at both the potential energy is, total energy is mgh. Now next part, as we have seen, the total energy at point B and C is mgh. So the total energy at point A, what will be there? So first of all, I'm saying that what is potential energy here? So you can see there is no height at point A in comparison to C. H is 0. So at point A, the potential energy is 0. Let's calculate what. So at point A, as H is equal to 0, this shows potential energy is 0. And what about kinetic energy? For that, let's see here. Here the velocity is 0 and velocity starts increasing and goes on increasing up to this point, because after this velocity goes to decrease. So this point has the maximum velocity. Let this point has maximum velocity, that is V. So what will be kinetic energy here? So kinetic energy is V square. Since this velocity is maximum, so we can say here V max. So kinetic energy is maximum here. So total energy again here, that is half mv square. I know you are seeing the different equations, that mgh here different and here is mv square, half mv square. The equations are different, but the energy will remain same. So again I'm saying the energy is at these 2 points and this at this point also, at every point, not only this only, at every point in between. This means here, or anywhere between these 2 points, among these 2 points, anywhere among these 3 points, you will find that the energy remains conserved. So as here the velocity is maximum, we can say what? We can say that at these 2 points, at these 2 points, the potential energy is maximum, kinetic energy is 0. But at this point, the kinetic energy is maximum and potential energy is 0. And in between, anywhere, the total energy is, either you are writing mgh or you are writing half mv square, will be acceptable. So we have completed our law of conservation of energy using this case also. Our next topic is energy dissipation or dissipation of energy. Suppose any machine is getting some energy, means you can say electrical energy, like fan. You are giving the electrical energy for fan to just give the wind energy. But with that wind energy, it is also generating the heat energy and sound energy. So we are not needing that sound and heat energy. So that form of energy is dissipation, dissipated energy. Like what? The same bulb. Suppose I'm switching on a bulb. What is the purpose of switching bulb? Just to take light energy. But along with the light energy, it gives some heat energy. So we don't need the heat energy. This is called dissipated energy. So definition says the energy transformed from useful form to useless form. Useful form to useless form is known as energy dissipation. And our next topic is the conversion of energy, means the conversion from one form to the another. As we know that this follows the law of conservation of energy, and many more examples are there, like mobile phone. You can take in the mobile phone, the speaker converts the electrical signal from the mobile and converts to the sound energy. In the same way, microphone, using that microphone you are speaking to, speaking in the form of sound energy, and that mic converts into the electrical energy. Like bulb, electrical energy to light energy, and many more examples are there. There are many conversions are there. Just go through the book. If you're facing problem, inform me. And next thing is, many students have given some query about the practice problems, but you're not putting the chapter number. Suppose you're saying practice problem 4. Every chapter has practice problem 4. How to query now? First of all, write chapter number, then practice problem number, then question number. Follow this pattern. And I'm just solving the question in randomly because somebody has asked some question but there is no information. I'm just putting randomly some questions. Next practice problem is 10 and the question 1. The heart of a normal person beats 72 times in a minute and does work of 1 joule per beat. What is the power of heart? So to calculate power, we have the equation power is equal to work upon time. Work is given 1 joule per beat. The work done is 1 joule per beat. And how many beats? 72 times. So if it is 1 beat, so 1 joule work is done. 72 beats means 72 joule work is done. So we will write here 72 joule work is done. And this is done in how many time? How much time? In a minute. means 60 second. So 60 on dividing that, what you will get, power is equal to 1.2 watt. Okay, again, 1 joule per beat means 1 beat means 1 joule work is done. 72 times beat means 72 joule of work. So you can do that. Our next question from PP11, practice problem 11, question 1. A beam of electron has an energy of 1 joule. How many electrons are there in a beam? So given that 1 electron volt is equal to 1.6 into 10 to the power minus 16 joule. So if there is 1 electron, so this much of energy. So I'm writing this equation that 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. Taking this on this side, so 1 upon 1.6 into 10 to the power minus 19 electron volt is equal to 1 joule. The 1 is remaining here. On reciprocaling it, you know that what will happen, 6.25 into 10 to the power 18 electron makes 1 joule. So this is the potential difference only. How many electrons are there? This much. So 1 joule has 6.25 into 10 to the power 18 electron. Number of electron is this. Now practice problem 13, question number 2. So the question says, a lead pellet of mass 10 gram leaves an air gun with a velocity of 40 meter per second. What is the magnitude of potential energy stored in the spring? So first of all, write what is given here. In this type of question, you must be confused that velocity is given, mass is given, so we can calculate kinetic energy, but the question is asking potential energy. So don't be scared about that because by the law of conservation of energy, whatever the kinetic energy is coming in this palette was from the potential energy, because you know the energy remains conserved. So whatever the kinetic energy is possessed by this palette will be exactly equal to the potential energy. So you can write here also, by the law of conservation of energy, the potential energy will be equal to the kinetic energy, and we are going to calculate kinetic energy. Let's do first. As I have written here, according to law of conservation of energy, potential energy of the spring will be equal to the kinetic energy in the palette. So the kinetic energy is equal to half m square. Half mass is 10 gram. So I have converted into SI unit, 10 upon 1000 converted to kilogram, and 40 velocity square. On doing further. So finally, potential energy is equal to. Potential energy is equal to 8 joule. But in the book it is given 16 joule. That is incorrect answer. Here we are completing our chapter 2. Again I'm saying, do solve the numericals. If you're facing problem, do comment and I'll solve your questions. And till then, for the starting of chapter 3, thank you.